Okay, Assalamualaikum and hello. We continue with electromagnetic induction. So Faraday has made a great discovery on electromagnetic induction, namely the method of conducting electric current with the aid of flux. Okay, so what is this means that you have a magnetic flux here. Okay, you have a magnetic flux. Okay, from this magnetic flux, you produce a current. Okay, so current. So basically from magnetic and magnetic to electrical. Okay, so cuts the magnetic flux and EMF is generated in the conductor. So you can see here, this is the flux. Okay, you have a flux here. Okay, something like this. Okay, you have flux and you're moving a coil. Okay, so the coil should be like that. Okay, something like this. So basically it will cut this flux. Okay, so cut this, and it will generate the EMF, electromotive force. So generate EMF means that this flux will become positive or negative. Okay, it will become something like a voltage source. So as a result, you can produce a current I. Okay, so it will something like this. So direction of the EMF. So when you want to determine this, you have to use a Fleming right hand rule. Okay, you have to use your right hand. Okay, so let me draw this. Okay, so you have right hand. Okay, you have sorry, I will draw the thumb first. Okay, this is okay. I cannot draw the hand. So basically, how to use a Fleming right hand rule, I think I already show you in the first lecture. So this is basically the motion of the inductor. Okay, which is U. If all back then we use direction. This is the flux direction. Remember, flux direction is basically from north to south when it is outside. Okay, something like this. So recall back and remember this one. If they use this, flux goes into paper, and you have something like it means out of paper. So make sure you know the direction. This one apply for not only for flux but also the U, and of course this one is the EMF. Okay, so basically this is the direction of current. Okay, so this thing is applied for all. So I, flux, and U. Okay, so EMF. Okay, electromotive force. So something like this. So the Lenz's law states that the direction of current induced EMF is such that it is tend to set out the current opposed to the motion magnetic flux. Okay, this one is just Lenz's law shows that the EMF produced is the opposite of the flux. Yeah. Okay, so you just to memorize it. Okay, the definition. So basically the explanation is just the flux produced, the EMF produced is just opposite to the flux. Okay, so next is if the conductor cuts or is cut by the flux, okay, at dt, then the EMF generated. So this one I already explained it. The average of EMF is 1 turn is okay. Sorry, I think this one has problem with the slide. Let me restart it. So this one is incomplete. So next, okay, so this is the equation of the EMF induced in electrical circuit. The inductance. Okay, this one is self-inductance. The unit is Henry. Okay, so you can call it 2 millihenry, 3 millihenry, is something like this. So E is equals to L, negative L di over dt. So if you look here, you can relate. Okay, remember, recall back the E equals to N d flux over dt. So recall back, and then you equals to, okay, this one don't forget the negative because of the Lenz's law, d di over dt. So basically L is basically N d flux over di. Okay, change of flux over change of I. Okay, so this is self-inductance. So flux is basically F over S. Go recall back. So remember F equal to Ni equals to S flux. So this is from this. Okay, and of course this one S. Okay, recall back. And then this is the self-inductance at A and B. So if you recall the formula you derived before, so L equals to N flux d flux over di. Okay, so self-inductance at the one side is LA. Okay, self-inductance means that each has their own self-inductance. Okay, what it means that if you have this one, okay, something like this. Okay, this one is at L1 LA, this one is LB. This is self-inductance. Okay, after this you will learn about mutual inductance. So focus on the self-inductance first. So N A, number of turn in N coil A, flux at A divided by current at A. Okay, so okay, so recall back this one. Sorry, not this one. Okay, equals to, you multiply by NA, so this one is basically 1. So NA squared flux A divided by NA IA, so equals to, okay, flux over S, you can see here. Okay, flux over S is flux, sorry, F, okay, this one, okay, and I, okay, divided by flux is basically 1 over S, so that's why it become N squared A over S. Okay, so recall back the magnetic circuit of the reluctant, so you get the self inductance here. So LA is basically this one. Okay, next you look at the self inductance at B side. So the same concept, use the same concept, LB, okay, equals to NB flux B divided by IB. So use this one and B squared divided by S. Okay, this one is the reluctant. So this is how you calculate the self-inductance. Now we move on to the mutual inductance. Okay. Okay, so you already see the self-inductance at A and B. Okay, so how about the mutual inductance? Okay, so this one, let me remove it. Okay, so mutual inductance, so you see that the L is equals to N flux divided by I. Okay, so if at A, okay, so LA and A flux A divided by IA. Okay, so this is self. Okay, self-inductance. Okay, how about mutual inductance? Okay, sorry, the pen is not responding well with the writing. Okay, so when it comes to mutual, means that you have to consider both. Okay, so mutual usually we use M. So mutual is basically we want to find the at flux A divided by IA, but at the winding B. Okay, so something like this. So M is equals to NB flux A IA. So it is mutual. You have the current at A and you find the flux at A goes to B and want to find the mutual inductance. So for mutual inductance we use S. Okay, so before I continue this is, so if you recall back here, okay, so you can see that reluctant here and here are the same. So that's why you can use S is equals to I A N A divided by flux A, or equals to IB and B divided by flux B. Okay, so this is self. Okay, self. Okay, this one is reluctant. Okay, because the reluctant is the same, you can see here the circuit has the same circuit. Okay, so we continue with the mutual. So you can see here, okay, this one is the mutual. Okay, so if you multiply here NA and NA, so you have NA and B flux A divided by IA and A. Okay, so if you recall back, S is equals to flux over Ni. Okay, so flux over S is equals to Ni, divided by flux. So if you look here, flux divided by Ni, flux A Na Ia is equals to 1 over S. So you have Na and B over S. So this is mutual inductance. So the inductance caused by both. So you have a mutual self, self here, and mutual is basically the relationship between these two inductance. So based on this, so based on this, if you recall back, LA is basically NA squared divided by S, LB is basically NB squared divided by S. So if you multiply LA and LB, is basically almost the same, because this is NA squared, NB squared, you combine it together, it will become S squared. And this one is basically M squared. So if you square the M, is something like this. So the mutual inductance, the M, is equals to square root of LA LB. So this is the quicker way to calculate it. So make sure you understand how to derive it. And what is the final equation for LA LB. And this one is also important. L equals to NDI dt. L is equal to NA and A flux A IA. This is for self, also the same as B. And of course the mutual inductance is M equals to square root of LA LB. And of course this one is flux leakage. Remember, recall back, there is some of the flux will be leak out. So you have to multiply by a constant. It's like a coefficient. So this coefficient is 0 to 1. 1 has no leakage flux, 0 has all leakage flux. K is equals to 1 when the magnetic leakage is 0. We continue with some practice with the mutual and self inductor. So you can see here there are ferromagnetic rings. So basically rings something like this. Have the cross-section area of A is equals to 800 millimeter squared. Of course you have to change it to SI unit. Okay, so equals to 8 by 10 negative 4 meter squared. Okay, and the radius means that this one to this one, okay, this is the mean radius. So this one is 100 and r is equal to 170 mm equals to 0.17 meter. So of course you have to find the length of this one. So L is equal to 2 pi r. Okay, let me check the recording first. Okay, so equals to 2 pi 0.17 is equals to so 1.07 meter. Okay, so this is the length. Okay, so you have winding connected in series, means that you have the first winding here, this is the second winding. So N1 is equals to 500, N2 is equals to 700. Okay, mu R relative permeability is 1200. Okay, so the calculation is find LA. Okay, sorry, it use L1, L2 self inductance and as well as the mutual inductance. So how to do this? You have to calculate the S first. Okay, so S is equals to L divided by mu naught mu R over A. So L is equals to 1.07 divided by mu naught 1200. Okay, and A is the 8. So 8 multiplied by 10 negative 4. So S is equals to, so S is equals to 886,957.24. Okay, so you get this, and then you just use the formula instead of the derivation. So remember, L1 is equals to N1 squared divided by S. So N1 squared is 500 divided by, don't forget squared, 886,957.24 is equals to okay, so this one is, sorry, let me use the calculator. So this one is 0.28282. Okay, Henry. Don't forget the unit, it is Henry. Okay, hash. So L2 is equals to N2 squared over S. So this one is 700 squared divided by 886,957.24. So you get 0.552 Henry. Okay, so this is how you calculate the self inductance. And now we move on to the mutual inductance. Okay, let me go upstairs. So mutual inductance is equals to square root of L1 L2. Just use the formula. So square root of 0.282. Okay, and then multiply by 0.552. Okay, so equals to, so you get 0.395. So Henry also the unit. So that is how you calculate the self and mutual inductance. Okay, so that's it for self and mutual inductance. We will continue with the next topic, which is energy storage in magnetic field. Okay, so we move on to the next part. Okay, energy stored in the magnetic field. Okay, which is also a part of the inductance. So you can see here, consider a current increase at a uniform rate in the coil having a constant inductance. So you have a constant inductance here. Okay, so recall back, E is basically negative L di dt. Okay, so of course the power. Okay, so P is power loss. Okay, power store is EI equals to IL di over dt. Okay, so Li di. Okay, so this one is the, if I is value of the current that is instant. Okay, so when it is instant, you just look at the I di, the change of current, no need to look at the time. So P is this one. So E is basically you integrate. Okay, integrate the P. Okay, integrate the P, you get L, because L is the constant. Integrate from I. Okay, I dt, I di. Okay, you get L divided by 2. Integrate. Okay, I squared. Okay, from 0 to I. Okay, so basically energy stored inside the magnetic field is 1 over 2 Li squared. Okay, energy is joule. Okay, so this is how you have to derive it. Okay, derive is usually in theory. So for this case, you have to memorize this. Okay, make sure you memorize this. Okay, so E is basically 1/2 Li squared. So of course L is equals to mu A n squared over L. Okay, so basically if you recall back, this is n squared over S. Okay, so from this, okay, E is equals this. So if you recall back here, okay, how I can move this. Okay, so you have here is L is this one. Okay, and of course hash is equals to Ni over L. So hash squared is equals to n squared I squared divided by L squared. So if you insert here, you can get E is equals to mu. Okay, energy mu hash squared area over L. This is another way to write this. Or of course the original one is 1 over 2 Li squared. So usually they will ask you how much is the energy stored in the magnetic field. You can either use this both formula. Okay, either you have which information you have to use either. Okay, you have completed chapter electromagnetism, which is topic 2A. So we will continue next with topic 2B, which is transformer. So that's it. Okay, thank you.